In 1981, the U.S. Air Force flew an aircraft that, by normal aerodynamics, had no right to feel safe. Sharp edges, flat facets, a shape that looked more like geometry than a plane. But the real shock wasn't that it could fly. It's what it did to radar. To a radar operator, a typical aircraft is simple. You transmit energy, it hits metal, and a clean echo comes back. That echo is information, distance, speed, heading. The F-117 changed the rules, not by making radar fail, by making the echo die. And the part most people miss is this. Stealth was never just shape. It was materials. A surface system engineered to absorb electromagnetic energy instead of reflecting it, turning a crisp radar return into heat and noise. For years, details of those coatings and structures weren't openly shareable. Not because of movie-style conspiracies, but because radar absorption performance depends on engineering specifics, composition, particle loading, thickness, layer structure, and manufacturing tolerance. And once you understand that, you realize why this story matters far beyond one plane. The same physics that once reduced a warplane's radar signature is now used to keep 5G systems stable, reduce electromagnetic interference in electronics, and build quieter electromagnetic environments in labs and test facilities. Stealth didn't make planes invisible. It taught materials how to destroy information. Now let's talk about why that knowledge was controlled and what exactly those black coatings were doing. If radar-absorbing skin were just paint, nobody would care. But radar is the backbone of modern detection and targeting. If you can reduce radar returns enough, you change the entire geometry of conflict. Who sees first, who decides when engagement happens, and who survives long enough to act. Here's the key. Radar absorption isn't a magic switch. It's a performance envelope. It depends on frequency, band angle of incidence of polarization, thickness, material composition, surface, smoothness, and edge treatment. And that's why the details matter. If an adversary understands what your material absorbs well and what it doesn't, they can adapt, shift bands, adjust waveforms, change sensor fusion strategies. So while the physics of absorption is public, the how to build it layer is strategically sensitive. There's also a second stake that matters in any advanced manufacturing story: process reality. A high-performance coating is not just chemistry. It's exposure control, repeatability, waste handling, and worker safety. When secrecy limits what can be discussed openly, it can complicate transparency around hazards and long-term handling. This episode isn't about conspiracy. It's about a real engineering trade-off: performance, secrecy, manufacturing complexity, and how technologies designed for war quietly become civilian infrastructure. Radar-absorbing materials didn't start with stealth jets. They started with a simple problem: metal reflects. During World War II, both sides experimented with ways to reduce radar reflections. Early approaches, rubbers, carbon-loaded coatings, resistive sheets, were heavy and limited, but they proved a concept. You could convert part of an incoming electromagnetic wave into heat instead of reflecting it. Then came the Cold War and a deeper realization: you could attack radar two ways. One, shape, to redirect reflections away from the emitter. Two, materials, to absorb what reflections remain. In the early 1960s, Soviet physicist Pyotr Yefimtsev published mathematical work describing how electromagnetic waves scatter from edges and surfaces. That research later influenced U.S. stealth design thinking, including work at Lockheed. But geometry alone could never be enough. A bare metal airframe still reflects. Even small hot spots, edges, joints, fasteners, can dominate radar return. So inside Lockheed Skunk Works' era of experimentation, the search wasn't only for a new shape. It was for a surface system that could drink radar energy. And that search led engineers back to something older than stealth itself: magnetic and resistive absorbers, materials that don't just reflect waves but dissipate them. To understand radar-absorbing materials, you only need one core idea. A radar wave carries energy in two coupled parts: an electric field and a magnetic field. Metals are excellent at reflecting electromagnetic waves because free electrons move easily and re-radiate the energy back, like a mirror. Absorbers aim to do the opposite. Let the wave enter the surface, then dissipate its energy internally. That dissipation can happen through different loss mechanisms. Two big ones are dielectric loss, energy loss through electric polarization, and internal friction in materials magnetic loss. Energy loss when magnetic domains or magnetic moments respond to wave and lag behind it. Iron-based particles are interesting because they can contribute magnetic loss at relevant frequencies. Under the right formulation, the magnetic component of the wave can drive microscopic magnetic responses that convert energy into heat, small amounts, but enough to reduce the reflected signal. But absorption alone isn't enough. If the wave reflects at the air, coating boundary, it never gets inside. So engineers design the outer surface to reduce reflection, often described as impedance matching. So more energy enters the absorber rather than bouncing off. Once inside, layered or graded structures can increase the chance the wave loses energy before it escapes back out. That's the physics. Now here's where the story becomes real engineering. The same physics that makes absorption possible also makes performance extremely sensitive to manufacturing details. Here's the part most people don't expect. The stealth problem was almost solved on paper and almost lost in the factory. Because once you move from equations to aircraft skin, tiny imperfections stop being tiny. If a coating's thickness varies, its absorption band shifts. If particles settle or clump, performance becomes patchy. If a surface ripples or edges aren't controlled, you get radar glints, small reflections that can dominate detection. And then there's mass. Many effective absorbers use dense fillers. If you load too much, you pay in weight. If you load too little, you lose absorption. Early stealth coatings and structures demanded something aerospace manufacturing wasn't built for at the time. Surfaces treated like precision electromagnetic components, not paint. So the real breakthrough wasn't a single ingredient. It was learning to manufacture absorption reliably, repeatably, on a full aircraft, in the real world, through weather, vibration, and maintenance. Stealth wasn't nearly defeated by radar. It was nearly defeated by variability. And that forced a shift that quietly changed aerospace manufacturing. Making radar-absorbing skin work meant treating the surface like a tuned system. Engineers had to control particle size distribution, loading fraction binder chemistry, and viscosity, layer thickness curing, and adhesion surface finish, and edge transitions. The goal was maximum absorption in general. It was targeted absorption across specific radar bands, with predictable behavior across angles and environmental conditions. That's why layer designs matter. A single uniform layer often reflects too much at the surface and absorbs too little internally. But a graded structure, lower effective reflectivity near the air interface, higher loss deeper in, can pull energy in and then dissipate it. This is the same general logic you see in anechoic chambers. You're not blocking waves. You're guiding them into a lossy path where they can't return coherently. And because the performance is sensitive, manufacturing becomes part of the physics. Process control isn't an afterthought. It's a mechanism that keeps the material acting like the equations predict. This is one of the clearest examples of an idea Future Forge returns to again and again. Advanced materials don't become real when they're invented. They become real when they become manufacturable. And stealth skin became one of the earliest proofs of that. But there's another side to manufacturability. The human and environmental costs of real processes, especially when secrecy limits outside scrutiny. Every black program has a visible side and an invisible side. The visible side is performance, aircraft that meet missions, signatures that drop, systems at work. The invisible side is the work required to build and maintain those surfaces. Repeated application, sanding, stripping, recoating, curing, waste handling, solvent exposure, and protective equipment. Even without dramatizing it, the hazard profile of many industrial coatings is not trivial, especially when you mix solvents, reactive hardeners, fine particulates, and aggressive cleaning cycles. In a normal industrial environment, exposure concerns can be discussed openly, MSDS sheets, workplace standards, independent audits. In a restricted environment, communication can be limited, sometimes for legitimate reasons, sometimes with real side effects. It can make medical documentation harder, and it can slow down accountability around best practices. So this isn't a gotcha story. It's a reminder. Advanced manufacturing always has two performance metrics. what the material does in the mission, and what the process does to the people who build it. Now here's the unexpected twist. Once the underlying absorption physics became broadly understood and manufacturing matured, radar-absorbing materials didn't stay locked to stealth aircraft. They spread fast. The public often thinks stealth materials are purely military, but the physics is too useful to stay in one domain. Modern electronics live in a world of interference. Packed antennas, dense circuit boards, high-speed processors, and crowded frequency bands. When signals reflect internally or couple between components, performance collapses, noise increases, timing degrades, false echoes appear. So absorption and shielding moved into civilian life. You see related absorber concepts in electromagnetic compatibility work, EMI/EMC, RF test environments, and anechoic chambers automotive sensing systems, where false echoes matter communications infrastructure, where reflections and coupling reduce performance margins. The headline isn't stealth paint is in your phone. The headline is the same engineering idea, control the wave, reduce the echo, kill interference, became a general tool. And once you frame it that way, you see why this story matters beyond history. A material designed to reduce detection became a material designed to improve clarity. But that spread raises real debates. Weight, cost, durability, environmental handling, and how much absorption is enough before it becomes over-engineering. Which brings us to the tension point. Radar-absorbing materials aren't magic, and they aren't free. First, performance is frequency dependent. What absorbs well in one band may be mediocre in another. That's why stealth is not a single number. It's a spectrum of compromises. Second, weight and thickness matter. Dense fillers improve absorption, but add mass. Thicker layers improve absorption, but affect aerodynamics, maintenance, and tolerances. Third, durability is hard. Coatings face weathering, erosion, temperature cycling, and mechanical damage. Even small defects can change electromagnetic performance. Fourth, manufacturing cost is real. When tolerances are tight and layer stacks are complex, production and maintenance become expensive. Finally, there's the safety and environmental side. Industrial chemistry requires controls, especially solvents and reactive systems. Even in civilian contexts, the question is always the same. How do you deliver performance without pushing hidden burdens onto workers or waste streams? So the debate isn't is absorption useful? It's, can we make it lighter, safer, more durable, and easier to manufacture at scale? That's where the next wave of materials engineering enters. Not just better fillers, but engineered structures, metamaterial-inspired designs, and microstructure absorbers that reduce dependence on heavy loading. The modern direction isn't to keep making coatings heavier and thicker. It's to make them smarter through structure, instead of relying purely on dense particle loading. Researchers explore engineered microstructures, patterns and architectures that shape how waves enter, scatter, and dissipate energy. This is where metamaterial thinking becomes relevant. Not science fiction cloaks, but practical electromagnetic design, structures that tune effective properties by geometry, not just chemistry. Even without going full metamaterial, incremental advances matter. Better control of particle dispersionless hazardous binder systems improve durability, and environmental stability manufacturing methods that improve repeatability and reduce manual variability. The theme is progress by engineering constraints, absorption that's lighter, coatings that are more stable, systems that perform consistently without extreme maintenance cycles. And as civilian electronics and sensing expand, 5G per 6G infrastructure, radar in vehicles, dense wireless systems, the demand for cleaner electromagnetic environments grows. So what began as a stealth problem has become a broader industrial problem. How do we control electromagnetic energy in crowded, complex systems? The next decade will answer that with a blend of materials science and manufacturing discipline, not secrecy. In the next 5 years, the biggest growth won't be in stealth aircraft alone. It will be in civilian systems that need electromagnetic control, communications hardware, sensors, labs, and high-density electronics. In 10 years, expect more integration, absorption, and shielding design into enclosures, boards, and structures from the start, less retrofit, more system-level engineering. In 20 years, The frontier may shift from absorb the wave to route the wave, controlling reflection, scattering, and coupling with engineered surfaces the way we already control heat with thermal materials. And the long-term vision isn't invisibility. It's electromagnetic predictability. Environments where signals behave the way you want, not the way geometry and interference force them to. Stealth is one chapter of that story. The bigger story is that we learn something fundamental. Information rides on waves. If you control the wave, you control the information. And that principle is going to matter more, not less, as the world becomes more sensor-driven. This story connects directly to the Future Forge universe. Radar absorbers sit at the intersection of composites and coatings, microstructure, control, process engineering, and metamaterials, where geometry becomes function. It's the same pattern you'll see in self-healing materials, high-performance ceramics, and next-gen manufacturing. A breakthrough doesn't become world-changing when it's invented. It becomes world-changing when it becomes repeatable, scalable, and safe. The stealth era forced aerospace to treat surfaces like engineered systems, not just paint. That mindset now shows up everywhere. From EMI shielding to advanced packaging to materials designed around signals, not just stress. If you're an engineer or student, the lesson here is simple and powerful. The secret wasn't a mysterious ingredient. The secret was that manufacturing precision became physics. Once you accept that, you start seeing modern engineering differently. The best technologies aren't only about discovery. They're about controlling variability so tightly that performance becomes dependable. And if you're not an engineer, this still matters because your entire world is becoming more electromagnetic. More antennas, more sensors, more wireless systems competing in the same space. So here's the question for you. Would you rather invest in materials that absorb interference, or in systems designed so interference never becomes a problem in the first place? The F-117 didn't turn invisible. It reduced the radar information that could come back. And it did that by treating materials as signal processing systems, surfaces engineered to take electromagnetic energy and turn it into harmless loss. That is the deeper takeaway. The future of materials science isn't only about strength, weight, or heat. It's also about controlling information, waves, signals, noise, and what survives measurement. And yes, some of this history lived behind restrictions for strategic reasons. But the long arc is clear. Once the underlying physics becomes broadly understood, the value migrates from secrecy to manufacturability, and the technology spreads. That's why radar-absorbing materials didn't stay in one aircraft program. They became part of the toolbox for modern electronics, sensing, and communications. This is what Future Forge Explored exists for, to trace that migration, how breakthroughs move from edge case programs into everyday reality, and what they cost, what they enable, and what they reshape. If you want to stay ahead of the materials that are building the next decade, subscribe. Because next, we're going deeper into another invisible technology that quietly controls your world. The materials that don't just absorb waves, they bend them. And once you see that, you'll never look at materials the same way again.